Now here goes a subject matter that I have not spoken about in depth for many, many years now, and that is the steam heating system. Before I get into the subject matter, let me start off running down my usual formation for those of you who have a particular interest in this subject matter. Then I want you to start off by getting my likes up. Give me the big thumbs up. Furthermore, share this production with somebody who might need to hear what I'm saying in this production. And for those who feel that they've gotten some sort of takeaway, tangible value and benefit from this particular subject matter, you can feel free to show your appreciation via the links in the description box. Now, with that being stated, the image that you are looking at, or the diagram that you are looking at, is a drawing that I got off of a YouTube channel, or screenshot, I should say, that I screenshot from a YouTube channel. Goes by the name of heathelp.com, or Heat Help, I believe it is. I believe the website, I think, is heathelp.com. The gentleman's name, I believe, is Dan. He has some pretty insightful information pertaining to heating systems, so I would advise that you go over there and take a look at his channel to get some pretty insightful information as well. Now, with that being stated, I'm going to be playing a clip of one of his videos that he's done. And what I'm going to be doing in this particular production is talking about air vents and the characteristics of air vents, especially when it comes down to the Hoffman and the Gordon and heat timer. Those will be the three particular air vents that I'm going to be giving you a breakdown of how these things actually work and what are their benefits or disadvantages based off of where you place them in your heating system. Let me also start off by saying this. You have many different channels and people that are going to give you advice when it comes down to your heating system. And listen, what I've come to understand is this is not a one-shoe-fits-all scenario. I've come to realize it's just never like that in life, just generally speaking. But regardless of whatever advice that anybody else can give you, whatever advice you might read out of a book, whatever insight that I can give you here on this channel, the best piece of advice that I can tell you is know your heating system. That is the best piece of advice that I can give you, because I can recommend that you do things one way and it might not necessarily be applicable for your particular and unique set of circumstances. And it doesn't matter how good or how long somebody's been in the field, if they have not stepped foot in your home to know what's taking place, or your building or your facility, they might not necessarily know what actually works for that particular system. So once again, the best piece of advice that I'm going to give you is for you to know your heating system. And this is mainly for people who, well, I guess I can leave it at that. But now, with that being stated, what I'm going to do is I'm going to play bits of his video. Well, I don't think I'm going to play the whole thing, but I'll play a segment of his video. And then what I'll be doing is giving you my perspective when it comes down to air vents. Now, let me also just go ahead and tell you that the information or the insight that I'm going to give you on these air vents is not based off of anything that I read out of a book. This is not based off of me sitting down talking with somebody who works in the heating industry, but this is based off of years of experience of me actually collecting air vents, these particular air vents, since I was in my teenage years, and based off of tests that I've conducted for myself. So what I'm telling you pertaining to how these things work, I'm going off of tests that I've actually done to be able to get these results. So with that, without furthermore, let me just go ahead and get right into his video clip.
About this part, because it's probably the most important stuff in all of steam heating, is venting. Because steam and air are gases that have different densities. Where there is air, steam will not go. So we got to be able to vent the system every time it starts up. So let's talk about the air vents. This is a very common air vent that's made by Hoffman Specialty. It's called a number 40, and I show it to you because there's so many of them out there. Now, it's got this little piece that sticks inside the radiator that is appropriately called a tongue. And the tongue is there to let the condensate that gets stuck in the trap in the radiator vent to drain out. It just dribbles along the bottom of the tongue back into the radiator. This is a float that has a flexible bottom, and the float is partly filled with a mixture of alcohol and water, and it's sealed. And when steam hits this, it causes the stuff on the inside to boil. And when that boils, it expands and it pushes the bottom part out, so the bottom pops out and it drives the pin up into the seat. At this point, the vent is closed. And this is kind of like hanging in space because it's sitting up there. And even when it cools up, it's still hanging in space because the steam pressure is pushing against the bottom of it, keeping it closed. So what we want to happen is the float to fall so that we can have venting again. And that's where this thing called drop-away pressure comes in. Vent valve manufacturers in their literature, they call it either...
Let me pause this for a second. What I will say is this particular vent, there's two places that you'll see this particular vent. Usually on a self-standing cast iron radiator or even a cast iron element, also known as a cast iron convector. And I'm talking about the older cast iron elements that were made years ago. I think they're called ahk or RO. These are no longer even made. The real old antique. Some of y'all have seen them. Some of y'all know what I'm talking about. Some might have no clue of what I'm talking about. But these are the areas you would find this particular vent, or you might find it on a riser pipe, at the top of a riser pipe. In rare occasions, you might even see it on a steam main somewhere or on a return line somewhere. That's rare, but it does exist. And this particular vent, and what he mentioned, what I want to do is just say this. In this industry, when it comes down to the mechanical industry, the heating industry, just talk about this particular subject, you'll have many people who will tell you a whole bunch of things and overcomplicate things. Me, what I look to do is try to simplify things and just keep it as simple as possible. And just based off of where you would find, or the application you would find this particular air vent, this is a Hoffman, as he mentioned, a Hoffman number 40. You are most likely going to find this on self-standing cast iron radiators, or I could just say cast iron radiators or steel, not steel convectors, but a steel riser pipe. You don't have to worry about drop away pressure, not with this particular air vent. Just based off of where you would find it, which would be on a self-standing cast iron radiator, and just based off of how these radiators are constructed and the way this vent responds to their construction, the vent, if it's working as it's supposed to, will not stop venting that radiator until the radiator has sufficiently heated up. And by that time, you don't have to worry about any drop away pressure because the vent has already done its job. So now, with that being stated, let me finish playing what he's saying here. I might even bring it back just so we can get another listen to it.
Operating pressure or drop. So what we want to happen is the float to fall so that we can have venting again. And that's where this thing called drop away pressure comes in. Vent valve manufacturers in their literature, they call it either operating pressure or drop away pressure. And it's the pressure through which the system must cycle down at the end of every cycle. And that's where the pressure control comes in. So drop away pressure works like this. Let's say you're starting up and you got steam pressure. Like, so you get to 2 psi or 5 psi, whatever you're running. And you're pushing with relatively low pressure against a big wide bottom. And that is shutting the vent. Now that's being opposed by atmospheric pressure that's trying to fit in through this little hole. So it's kind of like when...
Just pause it again. And what I want to do is just take a note of the two pressures that he referenced. He referenced 2 to 5 psi. Now, just based off of my experiences and what I've seen, 2 to 3 psi is what you would typically find in a small residential cast iron boiler. Maybe a 3-section, maybe no more than 7 sections. They typically set these at about 2.5, 3 psi. In larger residential buildings or even commercial buildings, what you would typically find is 5 to 7 psi, and there's a reason why that's done. A lot of people are going to tell you, well, you don't need that much pressure. And, even listening to some of the gentleman, Dan's critique and his perspective, he'll reference 2 psi, say that's all that you need is 2 psi. But there's other reasons why larger buildings go or set their cutout to about 5 psi, because it's not necessarily that simple. This is pretty much whenever you deal with commercial boilers. And let me just briefly reference the whole thing with the commercial boilers. A cast iron residential boiler, you can set that. And I'm talking about one that heats up maybe let's say between a 1 to 3 family house or brownstone or townhouse or multiple dwelling, whatever you're dealing with. 1 to 3 families, let's just give that a rough estimate around. You would typically find them running at about 2 to 2.5, 3 psi. You can set those boilers a lot lower. And let me just go ahead and showcase something. And this video will probably end up being a little bit longer than what I anticipated. But here, what we're looking at here is a 300 horsepower Scotch Marine boiler. This is inside of a boiler plant. The burner that you were looking at on this boiler is an industrial combustion D series burner. This thing will burn whatever grade of fuel you put in it. It'll go all the way from 2 to 6 oil, or it even burn natural gas. Whatever you decide to put in it, it's capable of burning. With one of these boilers, okay, let me just first start off with the cast iron boiler. Oh, better yet, because I don't have a picture of a cast iron boiler, but what I can do is this. I can show you a picture of the boiler that I used to have when I lived as a superintendent. And this boiler here, I operated it at about what? Well, let me just give you a breakdown on this. This is an electric Steam Masters boiler, an HC18. It had 18 kilowatts, 3-phase, 208 volts. This thing was very powerful. It was, when I looked it up initially back in 2005 before I purchased it, I looked at the specs for it, and according to the specs, it was able to, these things are designed for heating up bathhouses and sauna rooms. 740 cubic feet is what this thing was capable of heating up. So I said, clearly, if this thing can do 740 cubic feet of steam, then clearly I should be able to get this with no problem to be able to heat up 5 radiators in a 3-bedroom apartment. So I had this boiler since 2005, and it ran 11 winters straight on me. And I'm bringing this up for a reason. The operating pressures of most steam systems don't go usually any higher than 5 to 7 psi, and that's commercial buildings. Private residential houses is typically about 2 to 3 psi, or in certain cases less. This one I ran here at 8 psi. Now I'm bringing this up for a reason, because once again, when I'm giving you this insight that I'm about to break down to you, this is not based off of an opinion. This is based off of my experiences. And this is just one example that showcases I'm not talking based off of some theory that I believe. I'm telling you what I know in this particular case. And the pressure limit, the cutout of where I set this to, was between 7.5 to 8 psi. I believe sometimes it even hit 8 psi. All right? So just keep that in mind. But there's another reason why I'm bringing it up in this particular scenario right now. Because what you see on this is a basic pressure troll. And I believe I set the cut in to 5 psi. Cut out at 7.5, 8 psi, cut back in at 5. That's pretty much where I set it. 5 was more than enough. Some might say, well, you didn't need 7.5 to 8 psi. Why go with that one? Well, it was just a matter of me being greedy. If I was going to be responsible for heating up 2 73-unit apartment buildings apiece, then you better believe I was going to be warm as well, considering the fact that my apartment had not a single radiator inside of it. And of course, with the more steam pressure that you have, that's the hotter your radiators get. And that's pretty much the only reason why I ran it at that pressure level. Now, I could have ran this thing at 2 psi and it would have ran just fine. But I ran it at about 7.5 to 8 psi. With this particular boiler, and even with a cast iron residential boiler, when it cuts out, the pressure is going to drop, and at some point, it's going to cut back in. Soon as the pressure control cuts it back in, this has an electric heating element, inside of it, and it immediately cuts back on and starts boiling water and steam again. So you don't have any pressure loss beyond the cutting. Same thing with a cast iron boiler. A cast iron boiler, you can set them at a lower pressure than a big commercial boiler, because when they cut back in, you might have a 15-second pre-purge before it actually ignites a fire. Now let's go back to this big monstrosity. With this particular boiler, I've given y'all a breakdown on it. As a matter of fact, just to take you back down memory lane, I did videos on this particular boiler here. Now, of course, when I first did my first video on this boiler, we weren't using an MM burner. It was a D series burner. Nonetheless, they're both IC burners, and just like the D series burner, this burner will burn any grade of fuel you put inside of it. But when it comes down to big commercial boilers, like this one right here, which really isn't the biggest, this is just 125 horsepower, but this thing here is a monster. We're talking about 300 horsepower, okay? These boilers have a lot of safety features on there and a whole lot of sequences that the burner must go through before it can even ignite a flame. And one of those sequences is called a pre-purge. And I told y'all about this over a decade ago. I'm talking about back in 2013. We're now in 2023. And the pre-purge, what it does is when the when a vapor stat, because these boilers have vapor stats on top of them instead of pressure controls. So when the vapor stat kicks back in at about, let's say, 4 psi, 3 psi, the burner does not immediately initiate a flame. The burner will run on pre-purge for at least a minute, depending on what kind of relay you have inside of this box over here. As a matter of fact, with this boiler here, it's either this one or one of the boilers I had in these buildings. Like I told you, it typically would be about a minute of a pre-purge of it just blowing air inside of the combustion chamber. And then the reason why it does that is to prevent or to push out gases that might be lingering in, so you don't have a blowback. But I've seen these things take even up to 2 minutes of just purging air inside of the combustion chamber. Now your boiler, this vessel right here, is nothing more but a big heat exchanger. Let's go back to this one. Inside of these doors are hundreds of fire tubes. Okay, it is nothing more but a big heat exchanger. And without a burner, your boiler is essentially heartless. So now, let's just say you got your cutout at 2 psi on this boiler, right? Your burner shuts off. Your burner has maybe a 30-second post-purge of just blowing cold air inside of the combustion chamber and inside of your tubes. Let's say the relay is 2 minutes, even a minute long is still a long period of time. Your your vapor stat kicks in and calls for heat again. The burner cycles up and it goes through its pre-purge phase. Now, the shortest you're going to get with a burner like this is a minute. You might get up to 2 minutes. So for a minute to 2 minutes straight, you have nothing but chilled air that's inside of this boiler room, blowing inside of your combustion chamber, blowing or cooling the tubes that are inside. And we know whenever you start to cool steam, what happens is the steam collapses, it condenses. So now any pressure that you have, how long do you think this thing will hold 2 psi for? First, you have to go through the post-purge once the cutout, once it reaches the cutout limit. That's going to be at least 30 seconds. Then it's going to wait maybe a couple of seconds or maybe a minute, and then she's going to kick back in again once she drops out. What is the cutting point that you have? If you have a cutout at 2 psi, what's your cutting set for? If your cutting is set for, let's say, 1 psi, half psi, guess what? By the time 2 minutes within one pass and this thing is just blowing air at a high fire air cycle, you done depleted your pressure. And even by the time the burner finally, or the igniter, the ignition, or the pilot kicks in, you got at least 2 to 4 seconds before you actually get a flame inside, or the burner starts to, initiate a main flame. And then when it initiates a main flame, it runs at about low fire for like the first 30 seconds. So throughout this entire time when it's going through this cycle, you have completely depleted your steam pressure. And if anybody knows anything about steam heating systems, what happens when a steam heating system stops? When everything dies down and the pressure is completely depleted, it doesn't just remain as it is, it then starts to generate a vacuum. Why does a vacuum get generated? Because the steam that's inside the system is now collecting and condensing back into water. And since there is nothing in there to fill that void, it creates a vacuum until air vents start to open back up again and pull air back inside of the system. So this is another reason why with big boilers, big commercial boilers, you never find them running at 2 psi. Now, there's ways you can do that, and I'm not going to get into explanations in this particular, well, I might as well just go ahead and say it. You can do that through your L91, and that's through a modulator that pretty much will reduce the flame and hold it at low fire, and therefore you can run it at 2 psi without having to actually cut out the flame. And that's the way I did it when I was a superintendent for a number of years. Here we go. As a matter of fact, I could zoom in right here. This switch right here, this is a manual auto switch. Whenever I was making steam, I would put it on auto. And auto, pretty much what it did is the flame would reduce and the burner would just hold the steam pressure at 2 psi, 2.5 psi, wherever I had it set. So now with that being stated, let me go ahead and get back into his video. I'm going to back it up some, so just in case I forgot anything.
PSI or 5 PSI, whatever you're running. And you're pushing with relatively low pressure against a big wide bottom.
Oh, let's just once again take quick note of the two pressures that he referenced. And these are the cutouts now he's talking about, 2 to 5 PSI. Now, I want you to go back and remember what I just told you when I showcased the picture of the electric Steam Masters boiler that I had when I was living as a superintendent, and how I ran this thing at 7 to 8 PSI. That was the cutout limit. Keep note of that. Okay.
And that is shutting the vent. Now, that's being opposed by atmospheric pressure that's trying to fit in through this little hole. So it's kind of like what makes a car lift in a garage work, right? You got a big surface, big piston, small piston. This is trying to push down. This is pushing up. So when you got steam pressure on here, if it's on there all the time, this is going to keep the vent closed. Stays closed all the time. That was the challenge that we had with that New York City housing project that was taking Con Edison steam, which came in at a constant pressure and never dropped. The constant pressure just held the vents closed. And before the air is out, the radiator's full of air. The steam's trying to get in. The radiator won't get hot because the air can't get out. So we want to lower the pressure.
Let me just pause it there. Okay, like I said, what I look to do is just simplify things. In the case here, I don't want you to get caught up with atmospheric pressure opposing this, and that's just nothing that you need to worry about ever when it comes down to an air vent. And like I said, one of the tendencies that a lot of people tend to do in this industry, or just the mechanical industry, period, is going to overdrive, explaining things and giving all of these scientific explanations that really amount to nothing. And let me just go ahead and say this. I'm not here critiquing this man's perspective. What I'm saying is I don't want people to get caught up with things that are going to hold no benefit to you. That's nothing that you need to worry about. That's nothing that you have to really dig your brain into. Now, I do want to talk about what he is mentioning here with as far as the vent being able to open back up again. What you have is let's just call it a thermostatic element inside of the air vent, just to simplify it. As he mentioned, it's filled partially with water and alcohol, and when the steam hits it, it brings it to a boil, causing the bottom of this to push up on this bottom piece of the air vent. And pretty much how this works is so if you're dealing with a cast iron radiator, the larger the radiator, the more air it's going to hold. depending on how the radiator actually heats up, and this is something else that why I tell you people need to understand the personalities of your system. Let me see if I can actually put forth an example for you. Okay, so when we talk about the personalities of heating systems and air vents, that's going to be based off of where this is located at in the system. Whether you were dealing with a commercial building, a large residential building, or whether you're dealing with a small private residential house, brownstone, or multiple dwelling or townhouse, something like that. So when you are dealing with small cast iron boilers, they typically run at a lower steam capacity, meaning they don't heat the building or the house as fast. The radiators usually take a lot longer to heat up. And typically what you're going to notice in residential houses is that the radiators, when the steam gets into the radiator, it's a slower process. It makes its way into the service valve. Let's just, the valve is not there because it's been removed, but there would normally be a valve there in its place. So the way it would work is the steam would come into the radiator through the service valve, make its way up the first section, and start slowly making its way to the back sections, working its way from the top and then working its way all the way back down to the bottom. I don't think I have an image of this particular radiator. I should have taken more pictures of it. However, I don't have it. But there is an opening here for an air vent at the lower portion of the radiator. And in this particular situation, this is what we're dealing with, a small residential, maybe 1 or 2 family home. The way you're going to notice these things heating up, it's going to be from the bottom, the first section, making its way up to the top, all the way to the back, and then slowly making its way back down. Your air vent's personalities or characteristics are typically going to be, once it heats up, usually the whole bottom of the radiator. Okay, let's try to get this out of here. Get that out of there. Usually by the time it gets down here, most of the radiator is pretty hot. So the air vent doesn't have too much venting to do. And just based off of the way the cast iron radiator is constructed and the fact that it's a radiator that holds its heat for a very long period of time, once that vent locks out, or once it has vented out all of the air out of the system, it's pretty much just going to stay locked out and you're not going to hear it again. And like I said, the only way you typically hear it again is if there's still some air pockets along the bottom portion of the radiator. So then you'll hear it opening up occasionally just to vent out that air. And once that successfully heats up, that vent locks out and you don't hear it again until the next time, until the heat shuts off and then cycles back on again. Now, if this radiator is in a commercial application, in a commercial building or a large residential building, or even a medium-sized residential building, or even a small residential building, depending on, usually, let's just say a building with a Scotch marine boiler. These boilers run at a much higher capacity. The steam volume that they produce is a lot greater than your smaller residential cast iron boilers. And what you're typically going to notice about the way these systems, or the way the personality or characteristics that develop in these particular systems, is the steam gets into the service vent, and typically what you're going to hear. Okay. On a residential, let's say you got the small cast iron boiler, and this is hooked up on a cast iron boiler, all right? The air vent, if it's a Hoffman air vent, chances are you probably won't even hear it at all when the boiler first starts producing steam. You probably won't even hear it until the steam actually gets into the vent and locks out, and then opens and locks out and does whatever it needs to do to properly vent out the radiator. Now, on a big building that has a Scotch marine boiler, you're going to hear this vent blowing out air before the steam ever gets into the radiator. You're probably going to hear this thing blowing out air probably 5 minutes prior to steam even getting inside of the radiator. Because like I told you, the Scotch marine boiler generates a much larger steam capacity, a much larger steam volume. So it's really just blowing steam through there at much greater rates than a smaller cast iron boiler. So you'll hear it. And the whole time it's doing this, that's just air blowing through it. As a matter of fact, when I was younger, in certain cases, I would just take the vent off the radiator and this thing would just blow out air, room temperature air, for a good couple of minutes before steam would ever even get into the service valve. Now, with a cast iron, well, I don't got to describe how you would, because you chances are you probably wouldn't hear it because they run at a much lower capacity. But the reason why I bring that up is with this particular radiator, how that would work is a steam would get into your service valve, and instead of it making its way to the top, it's going to make its way all the way to the back of the radiator. And this the first thing it's gunning for is a service valve. And it climbs its way up, gets into the service valve locks out. Excuse me, no. Not the service valve. I'm sorry, I'm confusing people. The air valve. So the steam comes into the service valve, makes its way through the lower portion of the radiator, goes all the way to the air vent locks out. But now you still have, 2/3 or more, 3/4 of the radiator still is filled with air. So what is the air vent going to do? The air vent's going to open back up, and it's going to start to vent out the air. Now, there's still steam inside of this portion of the radiator. This is typically going to be the first portion of the radiator that starts significantly heating up, along with this section right over here. And then it's going to just start simultaneously making its way through the radiator. And you'll probably notice where the midsection is the last portion to heat up. The bottom is hot, the top is hot, but the midsection is the last portion to heat up. And that's just based off of the way those systems are set up with the style boilers that they have. And when I was a superintendent, my cutout was at 5 psi. If I decided to put my burner on manual and not use my modulator motor, the L91, to reduce the flame and hold it at 2 psi, that thing will run at 5 psi, and the cutout, I put it to about 4, maybe 3.5 psi. And the air vent, these air vents, and this is another reason why I say I want people to take note of the pressure cutouts that he mentioned, which was between 2 to 5. At 5 psi, these vents would still open up. If the radiator wasn't hot, and in these buildings, I had some big lobby radiators. I'm talking about 3 feet tall, 8 inches deep, 15, 16 sections. One was even 18 sections long. So these things took a while to heat up. And the boiler could still build up pressure as these things were heating up, and the vents would not close, or they wouldn't close completely until the radiators heated up. And as a matter of fact, when he talks about the drop away pressure, this is just what I've observed in my heating system when I used to live in this apartment back in the days. The boiler that I had in my apartment, I set to cut out between 7.5 to 8 psi. And the air vents on the radiators, if those radiators weren't hot, it would continuously keep venting, but not to the point where it sounds ridiculous. It would just vent moderately, and to the point of where the boiler would cut out on pressure. And when the boiler would cut out on pressure, like I said, I had mine set to cut back in at 5 psi. So those vents would essentially stop. Once the pressure started dying down, the vents stopped. They locked out. And then when the boiler would kick back on again at 5 psi, and I'm talking about what was set in my apartment, those vents would start reopening again. So what he's mentioning when he says that, the vent, you want to worry about the drop away pressure and whatnot, in certain scenarios that's applicable, but not to that particular scenario that he's referring to. But let me get back to that video. As a matter of fact, this is even better. Now, what I've done is I've taken some images of air vents. Now, and I want to go ahead and make this perfectly clear. The information that I'm giving you is not based off of anything that I read out of a book. It's not based off of me having conversations with people, but this is based off of me conducting tests. All right? Just like I showed you the image of the boiler that I had that heated up a 3-bedroom apartment. Just by the way, that boiler, when I set that up, as a matter of fact, let me see if I can go back to that for a second. No, I hit the wrong button. Okay. When I first put this thing in, I piped the boiler in myself. I ran all the steam lines. I ran the return lines, did the Harford loop. All that was me. I had somebody come and do the electrical work, and this is a guy that I actually started off in the field with, who told me that this will never work. There's no way you're gonna build a one pipe steam heating system with a boiler on the same level. Well, the boiler wasn't on the same level. I had the radiators elevated, as I showcased in those videos back in those days. They were elevated on stands, but I think the tallest stand I might have had was maybe 2.5 feet in height. The boiler was about, let's say, 1.5 feet. So there really wasn't that much I was really working with as far as room, as far as the water meeting the steam to the wet return level. But I made it work, and I made this work. The system had ran for over a decade, 11 winters straight. I had this system working. Up until the day I was ready to move out of that place and when I took everything down, that system worked. So I made this happen. And once again, I'm just letting you know that this is based off of my experience, the knowledge that I'm giving you. So let's go back into the air vents for a second. All right. And I'm going to tell you why what he is describing is 100% inapplicable to a Hoffman number 40 air vent. What he's describing as far as, and just based off of the pressures that he mentioned, this would never work with a Hoffman air vent. And listen, I've tested air vents for years. There was a point in time when I was a teenager, and this goes all the way up to my teenage years, where I used to just collect these things and test them. And the reason why I collected a lot of them, because the older Hoffman air vents, anybody who knows this stuff knows that the older Hoffman air vents that were made years ago worked much better and lasted much longer than the current stuff that they produce right now. You got a Hoffman vent back then, you could have the Hoffman vent last 15, 25 years on you, and you don't got a problem with that. There's another reason why you could snatch one off of one radiator, put it onto another. As long as the opening is not blocked off, you got you a good vent. Maybe it might have some paint on it. Maybe it might not look as pretty, but it most likely works. And this is one of the things I've come to realize over the years with dealing with in this particular industry. So I would test a lot of these things. And since I had the means to do it, I did it. And what I did, as a matter of fact, is if I wanted to know if one of these vents was still working, I can test them on a radiator that was set up in my apartment. And now I'm running this system at 7.5 to 8 psi. That's the cutout. And if the vent stayed open and didn't close, and that boiler came in, cycled in and out, in and out, in and out, in and out, and that vent stayed open, guess what? I knew that vent wasn't working. Now, how could this be possible according to what he's mentioning about the drop away pressure and how you need this stuff set up? There's no way that I could run a system at 8 psi and this vent still stays open. There's no way. If what he was saying was true about this particular vent, then there's no way that I can get away with doing that. And I did this on a regular basis, testing these air vents. Now, once again, I want to make it clear. I'm not critiquing the man's work. I'm just giving you a different perspective and just based off of a different level of knowledge. What I might tell you, well, let me not get into that. Let me just say this much. Here's the reason why, I'll say this much. What he is saying is 100% inapplicable to this particular air vent right here. However, it is 100% applicable to the air vent right here. And that is the Gordon's number D. I'm going to explain the reason why this is. Here's a reason why, or better yet, have you ever tried blowing through one of these? Which I have, and I've saved you the trouble of doing so in case you want to find out. You don't have to necessarily do it yourself because I've already taken the time and saved you the trouble of doing it. But have you ever tried to blow through one of these? How much air do you think you can push through this opening? As a matter of fact, you probably would hurt your face trying to squeeze enough air through this thing, trying to push this float. Let's see, this thermostatic pin in the lock position. You would probably hurt yourself. As a matter of fact, there is one way you can trigger this pin to come up and give a false, cause it to falsely lock out. And that is if you turn it upside down. That's one way, or you put water inside of it, and that's another way. The water will cause the float to come right up. But those are the only two ways you're going to get that float to stay in the closed position. As a matter of fact, some of the older people that I knew back in the day, since they didn't want to tamper with the service valve because they knew the service valve on the radiator is just something that you don't regulate. It's there just to shut it off and pretty much fix whatever you got to fix and open it back up, or to isolate that radiator. So what they would do is they would turn this vent upside down. And by turning the Hoffman vent upside down, it would cause this thermostatic pin to get stuck in the closed position. And it would pretty much lock out or give the radiator an airlock, and no steam would be able to get into the radiator because it's airlocked now. Now, I don't recommend that you do this, but this is how some people did it back in the day. However, if you were to take this thing and turn it upside down and blow into it, you're going to notice you're going to get nothing coming through here. Now, if you try to keep that same air pressure on there and then turn it right side up, do you think this pin would stay locked? No, it's going to come right down. No matter how hard, no matter how much pressure you try to put on this thing, it's going to come right back down. What is the reason for this? Pretty simple. Take a look at the opening. This is the outlet, all right? How big do you think that outlet is? What, maybe a millimeter? 1.5 millimeters? No more than 2, I guarantee. The reason why you can never get that thermostatic float to go in the lock position is you don't have the outlet capacity. Now, some might say, but look at the inlet. You have an 1/8 inch inlet capacity. That should be more than enough to get this to blow up. Well, it doesn't really matter how much or how big the openings you have down here. If all you have is 1.5 millimeter diameter of an outlet, you're never going to be able to generate that wind capacity. And if you don't believe me and you think that, well, the 1/8 inch opening at the bottom should contradict what I'm saying, okay, as I told you a little while ago, when I was a superintendent, I had big lobby cast iron radiators. Some of these things were 15 or 16 to 18 sections apiece. What size would you say, and this is on a one pipe system, what size would you say that the service inlet should be on a one pipe system? I'll tell you what it is. The smallest I've ever seen is a 3/4 inch, and there's only one reason why you would find 3/4 inches service inlet for a one pipe system, and that's pretty much if you're using cast iron baseboard and they don't want to make or run it with 2 pipes. And it looks ugly as hell because then they put this excessively large pitch on the radiator, so one half of the radiator is literally dangling in the air. It looks ridiculous, but anyhow, that's beyond the point. But that's the only place you will find 3/4 inches. The standard size you would find on an inlet for a one pipe steam system on a cast iron radiator, or even a steel convector or whatever, is going to be 1 inch to 1.25 inches, all the way up to 2 inches. Now, lobby radiators that are 15 sections or longer, the average size that I had in those buildings was either 1 inch to 1.25 inches, and that was what was inside of the apartments. You go into the lobby radiators, you have much larger openings. The service valves were 1.5 inches, big old monsters. And you would figure, okay, if this theory would be true that, well, this opening here being larger should be enough to be able to generate enough wind capacity to where you can push the piston and cause it to stay in the closed position. No. And here's what I'm going to tell you. You would figure with the radiators in the lobby having the larger service valve openings that these radiators would heat up faster. They didn't. They heated up at the same pace with every other radiator. Because on those radiators, what I had, even if I decided to slap a Gordon D air vent on these things, they still heated up at the same pace. The steam got into the radiator faster, but it didn't heat up any faster as far as just the overall output of the radiator. It took the same amount of time. So what I'm saying is if you don't have the proper wind capacity or the outlet capacity, it doesn't matter how much you blow through here, you're just going to pressurize the inside of the valve. You're not going to be, and what this needs in order for this to be able to do what Dan is describing that it will do, it needs to have momentum pushing through here or moving through here. You don't even need pressure. You just need a large amount of wind momentum to be moving through here, and that would cause that to go up. But just the way this is constructed, this doesn't happen on Hoffman air vents, not on the 41. There are Hoffman air vents that are made for steam mains that have much larger openings where that is applicable, but not on this one. Now on the Gordons, on the other hand, when you look at the outlet, it's damn near identical to the inlet. So yeah, if you actually put your lips around this and blow on this as hard as you can, you probably don't even have to blow as hard as you can. This thing, the thermostatic contraption that's in here will get stuck in a closed position. And this is where it really gets interesting and why I say you got to pay attention to these air vents and know their personalities. This is how you need to know, or why you need to know where you should install these things and where you should not install these things. Let me go down more pictures. As I mentioned before, I've labeled them. So this is a Gordon number D. And these are both for self-standing cast iron radiators or cast iron convectors, depending on how they're set up. If you're talking about the older ones, you might be able to have it sitting flush, horizontal. The next one you have is a Gordon's number 4. All right. Now, like I told you, what Dan is describing is 100% applicable to the Gordon's number D. Why? Because you have the outlet capacity and you have the inlet capacity, or I should say the inlet capacity and the outlet capacity, just based off of the size of the opening. That's several millimeters in diameter, so you can blow wind through there with no problem. Now with the number 4, now this is the same thing that you've seen in the Hoffman. You got the inlet capacity, but you don't have the proper outlet capacity. So when it comes down to what he's describing about the radiators having a drop away pressure, if you're slapping this particular air vent on a cast iron radiator, you might have that problem. Because if it pressurizes, but usually, like I said, the way cast iron radiators are constructed, once they heat up, as long as they got steam inside of the system, it's consistent steam going into the service valve, into the radiator, and all the air has been vented out, that radiator probably is not going to cool down at all until you shut that boiler down. But I'll explain that more in another video. But this vent here would be more so used for a riser pipe. It serves better for a riser pipe. However, it might not be a bad idea to use this for a cast iron radiator that has a harder time heating up. And the reason why I say that is because, like I said, if it's a cast iron radiator, even with it not having the drop away pressure, just the way the radiators are set up, they'll hold the heat for a long period of time and you're not going to notice any heat loss. Also, the next thing what I've noticed about the Gordon's vents, they're very good vents, but in certain cases, they don't all seal the right way when these things heat up. So meaning that the valve can heat up, it'll lock out, but yet you'll still get steam slowly escaping through the outlet, which can be a good or bad thing because you still can, you can keep your radiator vented, but depending on how much it's venting, you might be really just losing a lot of water or just stuff that you really don't need happening. This over here would be better for a radiator because it has a smaller outlet. And the way these things work, they work off of temperature. And if there's air mixed inside of the radiator, if there's air mixing into the same compartment of the radiator where this vent is located at, guess what? This vent is not going to close. Or it'll close, but it'll continuously keep venting, open and closing, or just gradually venting to let the air out. This is the personalities or the characteristics, I should say, of these vents. Slapping this on a riser pipe, it's actually the best place that it should be, just based off of the opening, and it doesn't listen to the thickness and the diameter of the riser pipes is typically 1.25 to 1.5 inches. So you don't have to worry about having any steam loss or whatever the case is, because just the way it's designed and the way it's constructed, the thickness of it alone, the steam generates its own flow. It just needs to be able to get to or get the air initially out of the system, and then it can generate its own flow. But once again, that's going to be for another video. So here we have a Gordon's number 1. And this is what you should find on a steam main. And let me just go ahead and say this much. Under no circumstances should you be using, and this is a straight air vent. So you would figure, this would be excellent for a convector. Well, you might be able to do that if it's a cast iron convector. you have a better shot. Why? Just the fact that it's a cast iron radiator, they hold the heat better, and it allows steam to flow through it easier without losing temperature the same way. However, under no circumstances should this air vent be used on a steel convector. Why? I'm going to tell you why. I did videos on steel convectors years ago. They're still up. You can go ahead and you can take a look at them. Steel convectors do not hold the heat the same way. Steel convectors will cool down significantly faster. What you'll notice about a steel convector, one of its advantages is that it heats up excessively fast. If all you have in your heating system are steel convectors, guess what? Your boiler is going to build up pressure fast. She's going to reach her cutout. She's going to shut down. She's going to kick back on when they cut in, and she's going to continue to repeat this process until the call for heat has been satisfied. But steel convectors, like I stated, once the call for heat has been satisfied and the heat shuts off, those radiators are going to start to cool down. And it's just based off of the way they're constructed. They have small steam columns or tubes that run through it, depending on how many tubes might be running through it. Might be maybe 3, 2, maybe 4, depending on the depth of the radiator. I'll tell you one thing. The wider the radiator, the bigger the depth of the radiator, that's the better the heat that it actually holds. So if you have an 8-inch steel convector, it's going to hold heat a lot better than a 2-inch steel convector or a 6-inch steel convector. A 2-inch steel convector will have 2 tubes, steam or water tubes running through it. A 6-inch steel convector will have 3 tubes running through it. An 8-inch steel convector will have 4 tubes. And they even got some that are 10 inches deep, if I'm not mistaken. I think they has 5 tubes. But those are very rare. So with that being stated, the problem with the steel convectors and the video that I did years ago, as I'm sitting, and I'm actually sitting in the room right next to this thing, and the air vent was opening up or cycling in and out. And this is as the system was on. It was pressurized, everything. But the vent would cycle in and out periodically. And the reason why it would do that is because the convector would actually start to lose its temperature. And also just what I'm describing to you, if you look at that video that I showcased to you, which it had a Hoffman number 41. That was the air vent I used on that radiator. This actually is a little bit larger. The 41 is slightly larger than the number 40. The number 40 is what you would find sitting on a self-standing cast iron radiator. The number 41, you would typically find these on steel convectors or cast iron convectors. Now the opening is slightly larger, which would mean it actually has the means to carry just a bit more steam capacity or momentum inside of the body of the valve. And despite the fact that I was running at 8 psi with that system, the boiler was already cycling in and out. So pressure was already reached, and it was just cutting in and out and keeping up the call for heat. But yet the air vent still continued to vent, which actually does what when you think about it? What am I saying when I'm bringing this up? It actually contradicts what Dan was saying about this particular air vent, with it being locked out. Because if the pressure was enough to hold it up, then how do you explain the air vent cycling in and out under 7.5 psi to 8 psi? And now, based off of the pressures that he just mentioned, was 2 to 5 psi. Now I'm running in about, if you're talking about, well, I got to get all the numbers, but what I'm saying is it contradicts what he was saying. So let's go back into the Hoffman vent. Steel convectors don't hold the heat the same way. So they'll heat up fast, and what you notice is that thing will start heating up, and if you have a good air vent on it, it'll stay hot. And how it'll stay hot, you will periodically hear that vent opening up to allow cold steam out and fresh steam back inside the radiator. That's how it's going to stay hot. The steel convector, if you have a vent that doesn't work properly, I'm not going to even say work properly, but if you put on a crappy vent on the radiator, what you're going to notice is the radiator is going to heat up excessively fast. So you decide to go ahead and I'm going to get to this heat timer vent in just a minute. But if you decide to go, let's say a Gordon's air vent, right? A number 1. Because you figure, oh, it has a large opening and this radiator is going to heat up excessively fast. You don't need to worry about doing that for a steel convector because they don't hold large capacity, which is also another reason why they cool down so fast. They have a lower steam capacity and a lower water capacity than self-standing cast iron radiators. So you don't have to worry about putting the largest vent on there to get it to heat up. It won't be worth it. Because what happened with the Gordon's air vent, if you put a number 1 on there, the vent will heat up, or the radiator will heat up. The vent is going to lock out. And then at some point, if the system is running for a long period of time, it's going to start to pressurize. And when she pressurizes, that thermostatic element that's on the inside of the body of the vent, that's going to be forced into the closed position. So as long as there's pressure on that system, guess what? This thing will never drop back down. That's where you need to drop away pressure for this particular air vent, for this particular application. This is not applicable to this if it's on a riser pipe or if it's on a steam main. This is only if it's on some type of a convector that is not cast iron. So, the Hoffman air vents. All right, let's talk about the vertical air vents for the convectors. The best ones that should be used for steel convectors should be no more than 3/8 to 1/8. I believe this is an 1/8 inch diameter that I have right here. And these are vents that I still have in my possession. I still keep a few of them just for my own record, which I'm glad I do either way. But these should be the only ones that should be used on the steel convectors. Or if you're running copper convectors or some other type of convector that has a thinner type of metal. The reason why I say that is because the body of the valve. Hoffman vents are very good for radiators just based off of the body of the valve, the way it's designed. Because the temperature of the vent will fluctuate with the temperature of the radiator, which is what you want the vent to do. This is especially important when it comes down to convectors that are not cast iron based. Because if the vent holds heat longer than your actual convector, guess what? Your convector is going to cool down. And you're going to be sitting in a room that has fluctuating heat. 1 minute the radiator is piping hot, the next minute it's getting cold again. Like why is it hot 1 minute and the next minute I don't feel the same heat. So you're never going to get the temperature where you want it to be at the time frame that you want it to be at. The next thing, and this is where I say you got to know the personalities of the vents. This particular vent, the heat timer vent, I believe I still have a couple of these kicking around. I didn't pull any of them out to take pictures of them, so I just went to Google and screenshotted some images. And when you go ahead and you buy one of these vents, it's going to tell you finally a vent that performs just as good as it looks. And this is a relatively small air vent. And although it looks impressive, however, I'm going to tell you this is not the vent that you should be using on radiators. As a matter of fact, I'm kind of skeptical about these vents, period. I mean, you can put them on radiators, but I really don't recommend them like that. There's 2 reasons why I don't really recommend these particular air vents. You can use them on steam risers. However, I'm not too certain whether I would put this on a steam main. The reason being is the same. Everything that's described about this particular air vent, this thermostatic element, which is also a float, it's designed to go up into the lock position. If water gets inside of your radiator, this will lock out. Now, it might not seal all the water, but it'll at least reduce the water substantially so you don't have significant water damage. This is the way these vents are designed. This is the way every single vent that you see demonstrated or showcased in any of these images that I took, which is what this is in my archives, in my arsenal or roster, if you want to say. Every last one of these vents have that same thermostatic element inside of it, which also serves the purpose of being a float. This is why with the Gordon's number D, you can blow into it, and if you get a significant amount of wind volume going through it, you will lock the float in the closed position. It's the same with every last one of them, from the number 1 to the number D to the number 4. They all have that same thermostatic element, which also is a float. Likewise with the Hoffmans, both of them. But now the heat timer air vent. The first reason why I don't recommend using this on a radiator, and I remember when I first encountered having one of these in the home that I lived in. If water so happens to get inside of your radiator and it makes its way to the air vent, the most this thing has inside of it is a thermostatic element. And the only thing that'll cause that thermostatic element to lock out is temperature. So if steam hits the element, yes, it'll lock out. And even at times when it does that, depending on this, you'll see water literally spitting out of this for the first couple of seconds, which can be rather dangerous, is why I'm really kind of skeptical even about putting them on riser pipes if you have it facing toward the public. But the next thing is the body of the valve. What you'll notice when you get one of these valves, it's going to come in a nice, pretty packaging, nice orange box with some literature. Don't be fooled by that. Okay, I'm telling you this based off of experience. I got a couple of these things kicking around. I'm not impressed with them. What you'll notice when you take the valve out of the box is that the valve has a pretty significant amount of weight to it for such a small valve. It outweighs pretty much any other vent that I have, even the Gordon's number 1 that has a 3/4 inch opening. And the reason being for that is because the body of the air vent has a thick brass. Now, this is very problematic for you to have a vent that has a thick brass on a steel convector, a copper convector, aluminum, whatever type of convector that you have. If it's not a cast iron based convector, you should not be using this vent. Like I said, 2 reasons. Number 1, if water ever were to get inside of that radiator, this thing will keep spewing out water. And listen, just to give you a quick story. I lived in a house years ago, and we had, well, the first thing, I had this same vent on my radiator, which is a self-standing cast iron radiator. All the radiators were cast iron. The living room radiator, however, had problems where return water would get inside of it, and it would make its way and get in, and just eventually at some point the radiator would fill up and it was just spraying out water. Now look at the size of this opening. This thing will vent more air than a Gordon's number D or a Gordon's number 1 air vent. The opening is a lot larger, and if you have this thing, this shield that's supposed to be able to where you can set it to how wide you want it open. If you have it open all the way, guess what? This thing is what, maybe an inch, half inch, 3/4 of an inch in length. So you have that much water just spraying out of your radiator. It's not a good look. I mean, it'll ruin floors. It'll cause all kinds of damage. So this is part of the reason why I say you got to be careful with this particular air vent. I wouldn't go with one if you don't have to, but if you do, know where you should and shouldn't use it. If you're dealing with a room that's faulty or your system has a tendency to build up water, you probably don't want to go with this air vent. The next thing what I've noticed about this air vent is when they go bad, it typically just freezes and no air can get through it. And I had this problem happen in that home that I lived in for a whole winter straight. I didn't have heat in my room. Everything else got hot. I had nothing going on in my room. Now, occasionally, periodically, the radiator would heat up and then it would just start slowly dying down. And that was it. It wasn't until the next heating season where they decided to finally change the air vent, and then that problem was done for. But just based off of the thickness of this particular vent, as that steel convector, don't get me wrong, it'll heat your radiator up excessively fast. Once that steel convector gets heated up, it's going to lock out. And at some point, that convector is going to start to cool down. And it's going to cool down most likely faster than this air vent, because the air vent is not hollow on the inside. Also, the thermostatic element on the inside also is what helps to build up its matter of retaining its heat. And what I'm saying is you don't want an air vent that's going to retain its heat. You want an air vent that's going to quickly dissipate heat along with the radiator. Now, if the air vent's on the radiator, it should sustain the same temperature of the radiator. Why? Because it's a thinner metal of the radiator, but that's not the same case with this. And I've had situations where put them on a steel convector, and you have these problems. The radiator starts cooling down, and it takes too long before this thing finally realizes, oh shit, the temperature's cooled down. It's time to open back up and get the radiator hot again. Likewise, when it comes down to certain Hoffman air vents, the 3/4 inch opening, they got Hoffman air vents with a 3/4 inch opening. I think I might have one somewhere kicking around in this apartment where I'm at now. But just based off of, when you look at this bead over here that has the hexagon fitting, this is made out of a thicker brass. And if you have a 3/4 inch opening with thicker threads, that's even that much more brass that can hold heat. And we all know the thicker the metal, the better the metal is going to hold its heat. That's exactly why cast iron radiators hold their heat that much longer. They're thicker. They're made out of thicker metal, so it naturally holds more heat. Steel convectors aren't designed for that. They got these fins that steam and water does not actually enter the fins. It just passes through the tubes that allow to go through there, and it pretty much is just a means of just dissipating heat. But cast iron radiators will hold the heat better. And just to get back to the point I was making, the 3/4 inch vent will have in addition to this thick bead over here with the hexagon slot, it also will have this thick 3/4 inch threaded nipple. And that right there helps it to hold its heat. So therefore, if you slap this onto a radiator, a steel convector, chances are it's going to hold its temperature a little bit longer than the steel convector. And your radiator is going to start to cool down. And what you're going to have is fluctuating temperatures, not even fluctuating temperatures. What you're going to have, instead of your radiator being able to heat your room at the same rate that the heat timer or the thermostat has it calling for heat going, what you're going to notice is it's not going to heat up the same way. Because why? You have this constant fluctuating temperature, up and down, up and down, up and down with the radiator. Why? Because the vent itself is not the proper vent for it. This is why you want to stick with an air vent that has either an 1/8 inch opening or 3/8. That would be best for convectors. Now, as far as cast iron radiators, the best vents that I've seen thus far are the Hoffman. Or you can stick with the Gordon number 4, or they have another size that's a little bit larger than this. I got one somewhere. I just don't know where it's at, and I don't know the number off the top of my head. But these will vent your system or vent your radiator pretty well, and you won't have the problem of worrying about the float locking out or the thermostatic element locking out because of pressure. And I think I can get back into his video, and then I'll close this video out. All right, let's bring it back for a minute.
When you got steam pressure on here, if it's on there all the time, this is going to keep the vent closed. Stays closed all the time. That was the challenge that we had with that New York City housing project that was taking Con Edison steam, which came in at a constant pressure and never dropped. The constant pressure just held the vents closed. And before the air is out, the radiator's full of air. The steam's trying to get in. The radiator won't get hot because the air can't get out. So we want to lower the pressure.
All right. So I've given you the breakdown on what type of systems that you can run at a lower steam pressure at as far as the cutout. What type of boilers? I've given you the breakdown with large commercial Scotch Marine boilers. You don't want to set your cutout any lower than 5 psi. There's a reason why the engineers who install these systems or install these boilers set the cutout to 5 psi. It's going to be roughly between 5 to 7 psi. I've given you the breakdown on that. You should respect those rules. Because if you start doing something else, you're going to start running into different problems. In my opinion, it's just simply not worth it. Now, he mentioned something when it comes down to Con Edison steam in a New York City Housing Authority building. Now, this might be one of the last things that I touch base on before I close up this production. And he mentioned how there was a constant pressure and the air vents weren't able to lock. Now, there's a lot that's not being stated in what he's saying over here, so I don't really know how to gauge this. For instance, the first thing I would want to know, well, first of all, I've been inside the New York City Housing Authority buildings, and these are residential buildings, so I'm assuming he's talking about a residential building. The system that he's describing is a single pipe steam system, and these are open systems, which I have never seen a single pipe steam system in a New York City Housing Authority building. From what I've seen, these are ran off of a vacuum system. Anybody knows about a vacuum system? That is a 2-pipe closed system. There are no air vents on the radiators. I'm not saying that what he's saying isn't true. I'm just saying I haven't seen it, so there's a lot that I really can't really speak to on what he's necessarily saying. However, or the next thing is, I've never seen a New York City Housing Authority building purchase steam from Con Edison. New York City Housing Authority buildings, from what I've seen, have boiler plants, and that's how they get their steam. So like I said, there's a lot that's not being mentioned when he brings this up. So even when it comes down to this particular scenario, my question would be, what type of radiators were in this system. Now there are some buildings that purchase steam from Con Edison, and from the last I heard that this is extremely expensive, and a lot of these buildings really just want to stop dealing with Con Edison and just buy their own boilers and produce their own steam because it's just too expensive. But I've been in some of these buildings, and I've actually seen a building that had a single pipe steam system with cast iron radiators with a service valve at the bottom, the front, and an air vent at the rear, at the bottom part. I've seen some of these buildings. What I'm trying to figure out is what level of pressure was this building operating at? Because and the next thing is, what type of radiators were in these buildings? Were they steel convectors? Were they self-standing cast iron radiators? And if so, what type of air vents were on the radiators? Because that would better yet be able to determine what's actually taking place. Because like I said before, I've given you a breakdown of this Hoffman air vent. And I've ran this on a system that operated at 7.5 to 8 psi, and if the valves are still open up, if the radiator's not vented, guess what? The valve is still going to keep venting, even as it reaches 7.5, 8 psi. As a matter of fact, I told y'all that when the boiler actually would cut out, the vents would stop because there's no more pressure. And then when it would cut back in again, if that radiator still had air in it, or those radiators still had air in it, the vents would start venting all over again. This is just what I've experienced. This is not off of no book. This is what I've experienced. So there's a lot of stuff that's not being stated in these particular scenarios that it would really be interesting to see, or I wish you would explain it in a bit more detail. Let's continue. Let me bring it back for a second, but
so that which came in at a constant pressure and never dropped. The constant pressure just held the vents closed, and before the air is out, the radiator's full of air.
And that's just the next thing I'm curious about. A constant pressure. I mean, anytime you deal with steam, especially if you're talking about Con Edison steam, you are talking about steam that's running under the street at excessively high pressures. These are dangerously high pressures. Nothing that you can play with. And I remember talking to somebody who worked in the field and said, listen, when he used to work in the field, if one of those pipes burst or went in the room he was in, he wouldn't have time to escape before he would be completely scorched to a crisp in high pressure steam. So there's, like I said, once again, there's a lot of stuff that's not being mentioned here. Because when you talk about steam being at a constant pressure, these things have pressure trolls. I've been inside of these buildings, and there's always something to actually regulate the pressure or hold it or cut it out, so that way you don't have an excessive buildup of pressure. Now, when you're dealing with Con Edison steam, you can run that at even lower steam pressures, because why? You're not dealing with a boiler that has to do a pre-purge and post-purge cycle. So you don't have to worry about having a drop of pressure. You can pretty much keep it almost consistent. And if you're running it at 2 psi, once again, like I told you, 2 psi is not going to be enough to force this vent to stay in a closed position. Not even 7.5 to 8 pounds would be enough to force this to stay up. That's just not happening. So once again, there's a lot that I really would like to know that's not being explained. Anyhow, let's continue.
Steam's trying to get in, the radiator won't get hot because the air can't get out. So we want to lower the pressure so that the weight of this float can overcome the closing force and venting can continue beyond the first cycle. So that's called drop away pressure. We got to get below that point. Now, back in the day, companies like Hoffman Specialty made vents like this. Now, this was a main vent. Look at the size of this thing. It's 10 3/4 inches high with a 3/4 inch tapping. This is an air vent. This thing is like a car muffler. And you just imagine the massive amount of air that this thing could vent. And this was developed during the time when we began to move away from coal and toward the automatic fuels of oil first and then natural gas afterwards. Because those automatic fuels change things dramatically. Here's what I mean. When you start up a boiler, the steam's going to form. We're going to have an air vent down the end here, and they might put that Hoffman number 10 down there. And when the steam starts up, we want this to happen. We want the steam to move through the header.
Let's pause that for a second when he talks about the Hoffman number 10. Let me see if I can bring it back. Can I bring it back? Okay. I don't think I've ever seen this particular vent before, but I have seen some massive vents on some of these buildings. And what I want to say is this. The simpler you keep things, the better. One of the biggest problems that we have in society up to this day and even when it comes down to the heating industry, is everyone who has designed something for this particular industry wanted to do something different rather than do something that would universally work. And when you start doing that, I call that pretty much a dick swinging contest. Y'all all know what I'm talking about. But it really creates more problems than what it's worth. And when I looked at vents, I was thinking of getting a large steam main vent back when I was a superintendent. And we're talking about, this is probably around 2013. And I took a look at one. And it was a large event, not like this, but it was a large event. And when I looked at it back then, the price of this vent was a 3/4 inch opening or inlet. And the price of this vent was what? $75. $75 for a vent. That was insane. That was crazy to me back at that time. Now, when you think about it now, it's probably not even really a bad price, but that's what it was back then. Now, we know with the cost of inflation and everything taking place, that these things probably cost way more now. So now imagine you go ahead and say, oh, I'm going to get me one of these Hoffman number 10s, and you look at something that's 10 inches in length, the size of a car muffler. You're probably going to be paying $200 or $300 for one of these vents, maybe even more. And my question is for what? Because chances are some of these vents, I've seen some of them on hot water systems. You slap them water, they don't last that long. Before you know, you got to replace the damn vent. So you done spent several $100s now to go ahead and do something that a Gordon number 1 can do. So if you're going to go with a large vent for a steam system, for a main or a return, I would say stick with a Gordon's. Go with a Gordon's number 1. Or even if you feel that if that's not enough, okay, if you got a 3/4 inch opening, maybe make a small manifold and put 2 of them on there. But you start going along with stuff like this, spending money on things that really, okay, vents, but it doesn't last that long, and you got to. And if it goes bad, because now air vents are made like garbage, everything's come from Taiwan, so you're not getting nothing of quality now. So how often do you have to replace this vent? And you're spending, let's say the vent costs $500 a pop, and let's say 2 years from now you got to replace that same vent. You go to Gordon's vent. From what I've seen, the Gordons and the Hoffmans, these vents last many years. Well, the Hoffman not as long as they used to, but the Gordons still have some pretty good quality to them. So if you're going to go with anything, I would say stick with a Gordon's number 1, or D if you have to. But anyhow, let's continue.
Because those automatic fuels change things dramatically. Here's what I mean. When you start up a boiler, the steam's going to form. We're going to have an air vent down the end here, and they might put that Hoffman number 10 down there. And when the steam starts up, we want this to happen. We want the steam to move through the header, out into the system, and down that line. We want that to happen. Now, there was a system developed by the oil guys in the 1930s that they called master venting. And the original articles that these guys wrote are all on heatinghelp.com. If you want to read them, just drop me a line at dan@heatinghelp.com, and I'll point you right at them. But it was the oil guys complaining about how in the days of coal, they would pipe the coal boiler in a certain way. The coal boiler would often be near the street because that's where the coal...
You know what? I'm realizing this is getting a little bit too long. That particular segment of what he's talking about, what I think I'm going to do is I'm going to save that for another production. Because right now, the only thing I really want to deal with is just the personalities of these vents. So like I said, I'm probably going to do that in a later production. And there's a couple of things that I do want to mention or continue off of where he left off at. But for now, what I want to do is just keep this on the vents. And just for you to have an understanding of the particular vents that you should, or know their characteristics, to know where you should slap these things, where you should place them, and where they shouldn't be. So just to give you just a final recap before I close out. This is a Gordon's number D. You would typically find this on a self-standing cast iron radiator, which you have more leeway to be able to use this on a self-standing cast iron radiator. But what I would recommend, if you have a riser pipe that runs in adjacent to that cast iron radiator, then I would say it's probably best to try to slap that onto the riser pipe rather than slapping it onto the radiators. Here you have a Hoffman number 40. This is one of the main vents you should be using for self-standing cast iron radiators. Why? The body of the valve itself is not too thick, so meaning it doesn't hold its heat. You don't want your air vent holding its heat. You want your air vent to its temperature to modulate along or adapt along with the temperature of the radiator. You don't want the radiator doing something different and your air vent is doing something completely different. That's how you start having steam pressure still built up, but your radiator is cooled down, but your air vent is still nice and hot and says, hey, I don't need any heat, I'm good. So you don't want that. So the Hoffman vents are good for that. They adapt to the temperature of the radiator and they vent the radiator out accordingly. Once again, we have a Gordon number D, the same Gordon number D that you've seen sitting in the previous picture. A Gordon number D sitting beside a Gordon's number 4. A Gordon number 4, I recommend that you can use this on a radiator. You can actually use this to balance out certain radiators. In a case where you might have one section of your house or your building heating up faster than the other, you might want to put these smaller Gordon number 4s to slowly vent out those radiators that are heating up quicker. That way you can get the steam to where it has to go, or the harder places, faster. So these are very good for radiators, Gordon number 4. And there's also another one, but I don't have the picture of it, so I'm not going to talk about it. But these are good because, like I said, the steam pressure won't cause the float or the thermostatic element to get locked in a closed position. And this is based off of the outlet not having the outlet's capacity size. A Gordon number 4, a Gordon number D, which I've already explained, and a Gordon number 1. Gordon number 1, I primarily recommend using these on steam mains, at the end of a steam main preferably, or at the top of steam risers. These should not be used on steel convectors, aluminum convectors, or any type of convector that is not cast iron based. And even with a cast iron convector, I don't recommend that you use them either. If you have no choice but to slap it onto a cast iron convector, I recommend that you only do it for temporary usage and replace it first chance you can get a new valve. The Hoffman number 41. These are perfect for steel convectors. In certain cases, you might see these slapped on top of risers, which, depending on what's taking place with that riser, I don't recommend it. I would recommend a Gordon's vent. If it's an isolated riser, I don't recommend I would say don't use this at all. If it's an isolated riser, if the riser has radiators attached to it for the entire run or the entire height of the building, then you might be able to get away with this. But once again, this is excellent when it comes down to steel convectors, cast iron convectors. You pretty much won't find these on cast iron radiators unless you got a thermostatic valve or contraption on it, which that can work as well. Heat timer vents. Like I told you, you're going to read a bunch of BS and bullcrap about a valve that finally works as good as it looks, and that's a bunch of bullcrap. Do not fall for it. If you have to use this particular vent, I would recommend using it at the top of risers, and I would recommend angling the opening of the vent away from the public. So that way, because these things have the tendency to spit out scalding hot water that could get right on you. So it's best that you don't do that or have it facing toward the public. However, can you get away with using these on self-standing cast iron radiators? Yes, you can. Are they the best when it comes down to venting them? No, they're not. But however, you still can use it because just based off of the construction of the radiator and the fact that cast iron radiators hold their heat better. And once again, I do not recommend that you use these for steel convectors. First reason being is that the radiator builds up with water, and since the convector has a much smaller water and steam capacity, if there ever was a situation where water got inside of it, it's going to fill up a lot faster. Reason being number 2 is that the valve body is so thick and so heavy, it holds its heat a lot longer than what your standard air vent would hold the heat for. And your steel convector will actually begin to cool down based off of its construction a lot faster than this air vent, leaving you to have slower heat times. You can use on a cast iron convector if you so choose to. However, I really don't recommend them like that. They're not the best vents. They look nice. They got a nice feel to them. It's a nice thick body. However, they are not the best vents. And with that being stated, I think I'll do a follow-up on this. But until the next time, I will see you on the next production.